तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we shall consider about order relation. We have been considering binary relations on a set A. So, we consider binary relations on a set A. A transitive relation, a binary relation which is transitive defined on a set A is called an order relation if it helps to compare two elements of the set. Though we may not be able to compare all pairs of elements, some pairs of elements we may be able to compare, and such a relation, a transitive relation on a set A which helps us to compare elements of the set is called an order relation. We shall consider several order relations like the partial order, the quasi order, the linear order, well order, etc. First, let us see what is meant by a partial order. A binary relation R on a set A is a partial order if R is reflexive, antisymmetric and transitive. So, a partial order is a relation, a binary relation R if it is reflexive, antisymmetric and transitive, if it has got all these three properties. The ordered pair AR is a partially ordered set or a poset. So, we see that a binary relation R on a set A is a partial order if R is reflexive, antisymmetric and transitive. The ordered pair A and the relation R on A is a partially ordered set or called a poset. The relation R is said to be a partial order on A. Let us consider some examples of partial order. If you take some set, say B, and the power set of B, that is a set of all subsets of B, then this contained relation is a partial order, because you can compare two elements. For example, if B is equal to, say, ABCD, AB is one subset, ABD is another subset, this is contained in this, and such a relation is called a partial order. It is reflexive because AB is contained in AB. Let us see what the three properties. It is reflexive, it is antisymmetric, because if you take two subsets, S1 contained in S2 and S2 contained in S1, that would mean S1 is equal to S2, which is the definition of antisymmetry. And it will also satisfy the transitive property, because if S1 is contained in S2 and S2 is contained in S3, obviously S1 will be contained in S3. This is the definition for transitivity. So, this relation is reflexive, it is antisymmetric and transitive, and so this is a partial order, it is a partial order. And the set AR, that is here the set is the power set of a set B, and the relation is contained in, this is a poset. This example, it is a poset. You call it as a partially ordered set or a poset. Another example is the, take the set of non-negative integers and the less than or equal to relation. Here again, if you see, if A is an integer, non-negative integer, A will be less than or equal to A, and so the reflexive property is satisfied, it is reflexive. And you can see that it is antisymmetric. If A is less than or equal to B and B is less than or equal to A, this would imply A is equal to B. So, the antisymmetry property is also satisfied, antisymmetric. And obviously, if A is less than or equal to B and B is less than or equal to C, then from this you can conclude that A is less than or equal to C. So, the transitive property is also satisfied. So, this relation is reflexive, antisymmetric and transitive. So, the less than or equal to relation on the set of non-negative integers, you can also take set of integers, same thing will hold. So, this satisfies all these properties, and so it is called a poset or a partially ordered set. Now, let me take a simple example of a set of a relation. Take a set A, B, C, D, and a relation on the set represented like this: A, B, C, D, like this. So, this relation has ordered pairs. What are the ordered pairs here? A comma B, A comma C, B comma D, A comma D, then AA, BB, CC and DD. So, these are the ordered pairs in the relation represented by this diagram. Now, is it a partial order? You can see that you have self loops at every node. So, the reflexive property is satisfied, and antisymmetric means you can have between two nodes, you can have no arcs or arc in only one direction. You should not have in two directions. So, antisymmetry property is also satisfied. And is it a transitive relation? Here you find that from A to B, B to D you have. So, you also have A to D. So, the transitive property is also satisfied, and this is a partial order. Now, when we want to represent a partial order as a diagram, we usually do not write everything on the graph. As a diagram, when we want to represent a partial order, we will not write everything, we will not draw all the arcs, we will write only the minimum number of arcs. For example, we know that a partial order is reflexive. So, there will be self loop at every node, and it is not necessary to explicitly draw the self loop. So, usually a partial order is represented by means of a R dash. If R is a partial order, diagram only will represent R dash such that R dash star is equal to R. A relation R dash whose reflexive transitive closure will be R will be represented on the diagram. That is called a Hussey diagram or a poset diagram. Hussey diagram or a poset diagram. In this case, it will be represented like this. It will be represented like this: A to B, B to D and A to C. This is all, and you do not mark the arrows also here. The arrows are supposed to be directed like this, from below to above. The directions are like this. So, if you take the reflexive closure of this, you will have the self loops, and also if you take the transitive closure, because there is an arc from A to B and B to D, there is will be an arc from A to D. So, the whole thing is represented by means of a smaller relation R dash, and that too without the directed arcs, and we assume that the arcs are directed from below to above, and the smaller relations reflexive transitive closure is R. This is easier to draw. In this case there are only 4 elements in the set, so it may not make much difference, but in other cases it may make difference. So, it is easier to draw a diagram like this rather than the whole diagram with self loops and arcs and so on. Another example of that is, take the set of integers, the set A, to take from 1, 2, 3 up to 12 say, and A is related to B. The relation is defined like this: A is related to B if A divides you can very easily verify that this is a partial order, it is reflexive, and it will be antisymmetric, and it will be transitive. A will be each number divides itself. If A divides B and B divides A, that means A is equal to B. If A divides B and B divides C, then A will be dividing C. So, all the 3 properties, reflexive, antisymmetric and transitive, 3 properties are satisfied. So, this is a partial order on the set A containing integers from 1 to 12. How will you represent it as a Hasse diagram or a Poset diagram? One will be below that. 1 divides 2, it divides 3, and it divides 5, it divides 7, it divides 11, this is 2, 3, 5, we have to mark 6 more elements, 1, 2, 3, 4, 2 divides 4, so 4 will be like this. See, there is no arc between 1 and 4, but by transitivity 1 also divides 4, okay. Then 4 divides 8, 1, 2, 3, 4, 5, 6, 2 and 3 divide 6, so 6 will be somewhere here, 6. 2 divides 6, 3 divides 6, so it will be like this. Then what about 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 divides 9, so 9 will be marked like this. Then 10, 2 and 5 divide 10, so 10 you can mark somewhere here like this, and then 2 divides and 5 divides, you can mark at the same level, this level also you can mark. Then 11 is there, 12, 3 and 4, 6 also divides 12. So, 4 and 6 divide 12. So, 12 will be marked like this, 4 divides 12, 6 divides 12 and so on. So, this is the Poset diagram or the Hasse diagram for representing the partial order which contains the set A of integers from 1 to 12, and the underlying relation is A related to B if A divides B. So, you can easily see that 1 divides 2 and 1 divides 8 also, or maybe 2 divides 8, but you do not have a direct arc from 2 to 8, you have an arc from 2 to 4, then 4 to 8. These arcs are directed from below to above. So, like this the arcs are directed. You do not have a direct arc from 1 to 9, but 3 to 9. Similarly, 12 is divided by 3, 2, 6, 4, but you only draw the lines from 4 to 12 and 6 to 12. So, this is the way you draw a poset diagram or a Hasse diagram. Now, slightly, if you do not want to have the reflexive property, you define what is known as a quasi order. Let R be a binary relation on a set A. R is a quasi order if R is transitive and irreflexive. So, partial order, we were considering partial order. It has to satisfy 3 property: reflexive, antisymmetric, and transitive. A quasi order is almost similar to that. You have the reflexive, you have irreflexive instead of reflexive, that is no self loops, and this property also you will have, and you have the transitive property. We need not have to specify that antisymmetry property explicitly, because these two together will imply antisymmetry property. Let us see how it is. See, what is the definition of antisymmetry property? If x is related to y and y related to x, this means x is equal to y. This is the way antisymmetry property is defined. But you will see that if you have irreflexive property and transitive property, this will be always false. This will always be false, and we know that in an implication, if the premise is false, the implication is true. This is what we have seen in logic. And why is this always false? If you have x related to y and y related to x, then because the set has transitive property, from this you can conclude that x is related to x. But if it is irreflexive, for any x, x is not related to x if it is irreflexive. So, this is not correct, and so this is always false. If this is true, x will be related to x because of transitivity, which we know is not correct. So, the premise of this implication is always false, and because the premise is always false, the whole statement is true, and so the antisymmetry property will automatically hold. So, these two conditions together will imply this. Okay. So, a quasi order is a binary relation on a set A, which is irreflexive, antisymmetric, and transitive. Examples are, if you consider a set B, say, and the power set of the set B, and use, instead of containment, use proper containment. The relation is the proper containment. In this case, reflexive property will not hold. If it is containment, reflexive property will hold. If it is proper containment, reflexive property will not hold, so it will be irreflexive. The other two conditions, antisymmetry and transitive, will automatically hold. And if you take the set of non-negative integers or the set of integers and consider the relation less than, we have seen that less than or equal to is a partial adder. If you consider relation less than, then it will be a quasi adder, because it is not reflexive, it is irreflexive, and less than is antisymmetric and transitive. So, this is an example of a quasi adder. Some other examples of quasi adder are, you take the set of courses in a curriculum, and C1 related to C2, course 1 is related to course 2 if C1 is a prerequisite for C2. You consider the set of courses in some curriculum, and you define the relation R such that C1 is related to C2 if C1 is a prerequisite for C2. This is irreflexive, a course cannot be a prerequisite for itself, and it will be antisymmetric if, and because if C1 is a prerequisite to C2, obviously that C2 cannot be a prerequisite, so that sort of a premise will always be false in that antisymmetric condition. And what about transitive? If property, if C1 is a prerequisite for C2 and C2 is a prerequisite for C3, then C1 is obviously a prerequisite for course P3 also. So, this is a transitive relation, it is irreflexive and transitive, and so it is a quasi adder. Another example is, you want to sort of allocate the tasks in a big way. I mean, you have a number of tasks, you have to find out which one should be completed before other and so on. For such a thing, in operations research, you use what is known as a PERT diagram, and there it tells you which jobs can start after which job. Only after this job is completed, the other job can stop and so on, job can start and so on. So, in such a thing, you define a relation like x is related to y. If x has to be completed before y starts, then such a relation will again be irreflexive and transitive, and so it is an example of a partial adder. You come across such examples in several things, in practical use in several fields of life, though you may not realize that you are really using a partial adder or something. Technically, you may not use that word, but in several aspects of practical life and in several fields in computer science, you use this idea. So, with this relation, we have the following results. Let R be a binary relation on A, then if it is a quasi adder, it is irreflexive. So, if you add E to that, if the reflexive closure you take and add E, it will be a partial adder, obviously. Then if R is a partial adder, it will be reflexive, and if you take away the E, if you remove all the self loops, then R minus E will be irreflexive, and so it will be a quasi adder. So, from a quasi adder, you can very easily get a partial adder by adding E, and from a partial adder you can get a quasi adder by removing the self loops or by removing the elements of the equality relation E. Now, these two things we have considered. Sometimes some more conditions may be there. See, for example, in the case of that divides relation, in a partial adder you may be able to compare elements, but you may not be able to compare all the elements. Take for example this one which you considered. You know that 2 is related to 4, you know that 4 is related to 12 and so on, 4 divides 12. Some elements you are able to compare, but what can you say about say 7 and 9? There is no relationship, neither 7 is related to 9 or 9 is related to 7. There is no relationship between them. That is why this is called a partial adder. You cannot compare every pair of elements. So, only some pairs that relation exists. Now, if in a partial order you are able to compare every pair of elements, then it is called a linear order. See, when you are comparing two elements, you say in a partial order is usually denoted by this set A, and the relation is, you can use a less than or equal to symbol, but it is slightly different from the less than or equal to symbol. Usually it is denoted like this. The underlying set A is denoted like this, the relation is denoted like this. Usually when you write, it is slightly different from the less than or equal to, but you may, if you are not able to use this symbol, you can use less than or equal to also. It's slightly different from the less than or equal to symbol. Now, if you take any elements, you may be able to say A is less than or equal to B, or B is less than or equal to A. But in the partial order, this may not be possible to do like this for every pair of elements. But if you are able to do for every pair of elements, you say that A will be less than or equal to B, or B will be less than or equal to A, then that is called a linear order. It is called a linear order, and you say it is a chain. A partial order on a set A is a linear, sometimes you call it as a simple order, sometimes you call it as a total order, if either A is less than or equal to B or B is less than or equal to A, for every AB belonging to A. That is, if you take any two elements, you will be able to compare them. If that is a linear order on A, then the ordered pair A, that relation, partial order relation, is a linearly ordered set. It is called a linearly ordered set. This is called a linearly ordered set. Now, take the set of integers and the less than or equal to relation. You can take the less than relation also, less than or equal to relation, less than or equal to relation you take. You can write like this: 0, -1, -2, -3, 1, 2, etc. You can compare any two of them. Any two elements if you take, you will be able to compare. If you take the set of non-negative integers and the less than or equal to relation, it will be like this: 0, 1, 2, 3. It looks like a chain. The opposite diagram will look like a chain. That is why this name chain. This is again a linear order. But if you take the set B and all subsets of B, for example, take B to be A, B, C, D, and take all subsets of B and the contained relation. This is not a linear order, because for example, take AB and take BC. You cannot say this is contained in this or not this contains this. You cannot compare them. So, this is not a linear order. Now, let us see what is a well order, and before going to well order, we will see what is meant by a greatest element and what is the least element of a set. Let A and this relation be a partial be a poset. You have a partial order A and this like this, you have a partial order. I will read it as less than or equal to, though this you have to, it is slightly different from the less than or equal to symbol. I will read it as less than or equal to. A less than or equal to be a poset and B a subset of A. Then a element of B is the greatest element of B if for every element B dash belonging to B, B dash is less than or equal to B. An element B belonging to B is the least element of B if for every element B dash belonging to B, B is less than or equal to B dash. This is the definition. If I take an example, it should be more clear to you. Take the set A as the power set of a set having two elements. So, this has got and the contained relation. AB is one set, the empty set is 1, A alone is one subset, B alone is one subset. The poset diagram is defined like this. This is contained in this and this is contained in, obviously this is contained in this because of the transitivity. Now, if you look at the whole set, AB, this is the greatest element because every other element is less than that, and this is the smallest element here or the least element. This is the greatest element and this is the least element, but I do not consider any all of them. Suppose I consider only this and this, if I consider only this and this, among this you find that this is the greatest element because everything else is less than that, and this is the least element because this is less than every other element. Now, if I consider this a set consisting of only this and this, a subset consisting of a subset of A I am considering. B, the definition is with respect to a subset B of A. So, the subset has only these two elements. If you consider this, they cannot be compared. This is not less than this, nor this is less than that. And this subset has no greatest element because you cannot define an element with which you can compare these two and say that these two are less than that. So, if you take a subset having these two alone, this has no greatest element, neither it has got least element. It does not have a least element either. Okay. So, a greatest element may exist, a least element may exist or may not exist. So, after having defined, let us see what is. And if the element exists, if a greatest element or the least element exists, it is unique. Let A less than or equal to be a poset and B is contained in A, B is a subset of A, and if A and B are the greatest elements of B, suppose you are having two elements A and B as the greatest element, then A should be equal to B, or in other words the greatest element, if it exists, is unique. Why? Suppose I have two elements A and B, both of them are greatest elements A. Then by the definition of greatest element, A will be less than or equal to B, and because B is the greatest element, and by the definition of greatest element, because A is the greatest element, B will be less than or equal to A, in which case this will, from this you can conclude that A is equal to B. So, the greatest element, if it exists, is unique. The greatest element, if it exists, it need not exist, if it exists, is unique. Similarly, the least element, if it exists, is unique. Now, having defined the greatest element and the least element, we will see what happens. A binary relation R on A is a well order if R is a linear order and every non-empty subset of A has a least element. The ordered pair AR is called a well ordered set, and R is a well ordering of A. So, first we define partial order, quasi order, then we define linear order, and in this linear order if you put the restriction that every non-empty subset has a least element, then it is called a well order. Let us see some example. Consider the set of non-negative integers and the less than or equal to relation. You see, it can be represented by a Poset diagram like this 0, 1, 2, 3, etc. This is a well order, because if you take any subset that will have a least element, any subset you take that will have a least element. Instead of that, you take set of integers and the less than or equal to relation. The Poset diagram will look like this. It is not complete, it is like this 1, 2, minus 1, minus 2, like that. Now, if you take a subset, say all set of negative integers that has no least element, you cannot define the least element for that. So, this is not a well order, this is not a well order. Sometimes it may be very necessary to have a well order. If you have a linear order, it may not be sufficient, we may require a well order. A slightly different version of that we have studied in proving program correctness, which we considered earlier after logic portion. We considered that. There we defined what is known as a well founded set, that was slightly different, and the definition is slightly different from well ordered set, but there also the condition was that every subset should have a least element. So, you can see that n less than or equal to is a, if you take the set of non-negative integers and less than or equal to relation, that is a well ordered set, a well order. Now, we have considered set operations on sigma star, taking sigma star and defined some lexicographic ordering and so on. Now, before going into that, we saw that I less than or equal to is not a well order, but you can induce a well order on that, induce a well order on it, into it. How would you do it? See, here two integers a and b are compared like this, a less than or equal to b. The comparison is like this. Now, if you define the relation a less than or equal to b in this manner, so that a less than or equal to b, if mod of a is less than mod, the numerical value is less than b, if or if mod of a is equal to mod of b, a is less than b. Okay. If you define the relation like this, you can define a well order into the set of integers. It is like this. For example, if you do that 0, you will order the elements in this way. Minus 1 and 1 will be less than or equal to minus 2 and 2, because if the modulus, the value of that is less than the value of this, this will come before that. So, they will be ordered like this, and within them minus x and plus x, minus x will come because of this condition, minus x will come before plus x. So, minus 3 plus 3 like that, you can order them. So, this is the, you can say this is the first element, this is the second element, this is the third element, fourth, fifth, sixth, seventh, like that you can say. And if you define like this, you can compare any two of them. If you take again you can compare any of them, and also if you take any subset, that will have a least element in this case. But you must remember that the relation we are defining is not less than or equal to on the set of integer, but it is a relation R which is defined this way. A is related to B if the value of A is less than the value of B, numerical value of A is less than the numerical value of B, and if they are the same, A is less than B. So, if you define this relation, it becomes a well order, but not under less than or equal to. Okay. The next is we consider some operations on sigma star. What is sigma? Sigma star we have seen earlier. Sigma is an alphabet, and sigma star denotes the set of all strings over sigma. Where lambda or epsilon denotes the empty string, or lambda or epsilon denotes empty string of length 0. We have seen all this earlier, what is the length of a string and so on. On sigma star you can define two types of relation. One is called the lexicographic ordering and another is called the well ordering or canonical ordering. Let us see what is that. Let sigma be a finite alphabet with an associated alphabetic order. What do you mean by that? See, sigma is ABC, say here A comes before B, B comes before C, that is the associated order on it. So, generally you write ABC or you can write A1, A2, A3, which one is first, that you should mention clearly. And one point we have to note that all this linear order and well order, if you define on a finite set, then any linear order will be a well order, because it will always have a least element. A linear order on a finite set will be a finite chain like this. So, it will always be a well order, you will have the least element. Only on infinite set that problem will come. So, let sigma be a finite alphabet with an associated alphabetic linear order. If x belongs to sigma star, then x is less than or equal to y in the lexicographic ordering of sigma star. If x is a prefix of y, or x is equal to zu and y is equal to zv, where z is a string in sigma star and that is the longest prefix common to x and y, and the first symbol of u precedes the first symbol of v in the alphabetic order. It is lexicographic ordering is the same as the order followed in a dictionary. Okay. So, if you have two strings x, y, when do you say that x is less than or equal to y? X comes before y in the dictionary. Okay. That is possible when x is a prefix of y. That is, suppose I have a1, a2, an and another string a1, a2, an plus 1 something like that am. This will come before this in the dictionary. So, this x will come before y. This is x, say this is y. Otherwise, x is of the form, say some a1, a2, ai plus 1 etc. an. Y is of the form a1, a1 is the same as this and ai, up to ai it is the same, then bi plus 1 and so on, and this comes before this in the order, a comes before b, like that. In that case, you say x will come before y in the dictionary or x is less than or equal to y. This is the alphabetic ordering or the lexicographic ordering. Let us take some strings and compare. For example, take A, B, C, A, B, C, A, B, A. Which will come before this? This will come before this. If you want to arrange this, A will come before these, and among this A, B, A will come before A, B, A will come before A, B, C, and B, C will come afterwards. Okay. This is called the lexicographic ordering, or this is a linear order, isn't it? This is a linear order because if you take any two strings, you can always say that this string should come before the other string. So, it is an example of a linear order. For example, take sigma to be ABC. Okay. Then we have considered some strings. Is it a well order? It is a linear order is okay. Linear order. This is a linear order, right? Is it a well order? It is not a well order. Why? You cannot find the least element in a subset. If it well order means if you take a subset of that, it should have a least element. For example, consider this set B, AB, AAB, AAB, like that. Consider the set. That is A power NB, n greater than or equal to 0. Now, you can see that if you take AB, this will come before B, isn't it? And if you take AAB, that will come before this. And if you take AAB, that will come before that. But what is the least element? Which one is the least element here? This is less than this is less than that. What is the least element? There is no least element in this set. So, this is not a well order. In order to compensate for that, you define what is known as a well order on the set of alphabetic order. Let sigma be a finite alphabet with an associated alphabetic order, and let length of x, that mod of x denote the length of x, then x is less than or equal to y in the standard ordering of sigma star. If the length of x is less than or equal to y, or if the length of x is equal to length of y, then x precedes y in the alphabetic ordering or lexicographic ordering of sigma star. If you define this way, again you get a linear order, and not only that, you can talk about the least element in this order. So, take sigma to be, for example, take sigma to be ABC again. A comes before B, B comes before C. How will you talk about the other strings? Here you can arrange them in the order. First the empty string will come, then strings of length 1 will come, A, B, C, then strings of length 2 will come, and among them they will be arranged in the alphabetic order. So, strings of length, if you arrange AA, AB, AC, they will be in this order: BA, BB, BC, CA, CB, CC, and so on. If you take, say, ABB and ABACC, this will come before this, because the length of this is 3, the length of this is 4. Even though in the alphabetic order this will come before this, in the well order this will come before this, because the length of this is less than the length of this. And if you take two strings of the same length, ABC and say AC, A, something like that, which one will come first? This will come before that, because in the alphabetic ordering this will come before this. So, if you compare two strings, the smaller string will come before the larger lengthier string in this order, and if they are of same length, then the string which will appear in the alphabetic order first will come before the string which will appear later. Now, in this case consider the set B, A, B, A, B and so on. This will be the least element, is not it? This is of length 1, the rest of them are length more than that. So, that will be the least element. Since you can arrange them, you can talk about, you can arrange them into one corresponding with a set of non-negative integers 0, 1, 2, 3, 4, 5 and so on. So, you can arrange them in this order, and you can talk about the ith string in this enumeration. When you can do this, you can, it is always a well order. So, you can always talk about any subset you take, you can always talk about the least element of the set. So, this is a well order, and this is very important, because in many cases you may want to have an enumeration of the strings over the alphabet sigma. I will continue with this enumeration. Suppose I have a string x a, what will be the successor of x a? X b will be the successor of, okay, for x a what is the successor? What is the next string? It will be x b. For x b what will be the successor in this well order? It will be x c. For x c what is the successor? It will be y a, where y is the successor of x. And similarly, if we take the predecessor, for x b the predecessor will be x a, for x c the predecessor will be x b, x is some string say, and for the string x a the predecessor will be y c, where y is the predecessor of x. This is the way you define. You can arrange the strings of length 3 also here. This is, we have arranged the first strings of length 0, then 1, then 2. If you want to arrange strings of length 3, it will be in this order: AAA, AAB, AAC, AB, A, ABB, ABC and so on. So, you find that then ACA, ACA, ACB, ACC and so on. So, you find that XA, the successor of XA is XB, the successor of XB is XC, and the successor of say XA will be YC, where and the successor of XC will be YA, where Y is the successor of this AA. For AA, AB is the successor. This is what we have seen. So, from this example you can very easily see the successor of XA is XB, successor of XB is XC, but the successor of XC is YA, where Y is the successor of X, AB is the successor of AA. And similarly, you can see that the predecessor of XB is XA, the predecessor of XC is XB, and the predecessor of XA is YC, where Y is the predecessor of X. This is the way you define. So, you can arrange the strings in this order, and you can have a 1 to n mapping with the set of non-negative integers 0. You can talk about the ith string in the, supposing in this well order over the alphabet ABC, if I ask about what is the 47th string in the enumeration, you can always say, you can find out and tell what is the string and so on. and this sort of an idea is very useful in proving some very difficult theorems in automata theory about decidability. Okay. So, we shall see more about this ordering in the next lecture.